Hello everyone, welcome to AI Anytime channel. In this video, we are going to explore quantization of language models, large language models. Quantization is one of the most fascinating topics to discuss in the entire AI landscape, I will say. From a technology perspective, the algorithms are fascinating. If anybody who wants to go deeper into this in this field, they all should focus on quantization techniques because quantization will help this technology to be adopted in the enterprise level or to be adopted and go mainstream. Nobody has a 100 GPU or a larger GPU to kind of inference or fine tune or so on and so forth. But quantization can help you run or inference these language models or a large language model or MOE or multimodal model, whatever you call it, on a CPU machine, on mobile devices, on an edge device. Only quantization can do it so far. Okay, so you should be aware of basics of quantization. Nowadays, using one line of command, one line of code, you can quantize a model. But what about the fundamentals of quantization? Do you really know what quantization is? How many different types of quantizations are there? How to quantize a layer? What kind of activation functions that you can quantize, and so on and so forth. So this video is for beginners. This video is for anybody who has not in-depth knowledge of quantization, but even for people who have used Llama CPP or OLlama or Optimum or Auto-GPTQ kind of a tool, this video is also for you because it's not only about writing one line of code and converting it, a model from SIP tensors to GGUF or things like that, right? You should have the understanding of quantization and quantization techniques and algorithms. That's what I'm going to cover. We'll start from a simple neural networks, then we'll go into a transformers BERT based model, then we go into a GPT-2 model, and then we go into a Phi 3 model. So we'll increase the complexity throughout the video, and we'll also cover a lot of theoretical aspects, mathematical intuitions behind quantization. So I'll recommend you to watch this video completely if you really want to master and learn quantization. If you don't want to do that, skip the theoretical part and then just go into the code part. Okay. Now, without any delay, let's jump into and see what quantization is and how we can leverage it in our journey. All right, so let's start our experimentation with the basics of quantization. And I'm going to explain a few things before we jump into the code, I think, which is important for all of you to understand. So I'm writing here called quantization, and we'll give you a brief overview of quantizations and common quantization techniques. Probably you're already aware, the GGUF format or GGML or GPTQ and all these fancy names, but I think you should be aware of the fundamentals before jumping into these words. So we'll first talk about it. Then what do you mean by quantization and overview of quantizations and so on and so forth. So when you talk about language models such as GPT-2 or Llama 3 or any other models, so quantization is basically a technique that used to reduce the precision of the numbers. Numbers are nothing but the weights and biases that represent the model. The only two regions that we do it, one is to decrease the model size. So let me just write the important thing here. We quantize model to decrease the model size. And once you decrease the model size, you are just speeding up the computation power. Okay. So I'm just going to write up speed up here. Okay. So speed up computation. Not everybody has A100 or L4 or T4 GPUs, right? So a lot of you would like to run this on consumer grade GPU or a CPU kind of a thing, and that's where we use quantized models. So keep this in mind: decreasing the model size and speeding up the computations. That's what we and keeping the we'll try to keep the performance as it is. We'll show you how when the complexity increases, performance of course degrades. So when people say that, hey, look, quantization does not affect your performance, don't trust it. Nobody can prove it to be honest. We like to see with a simple neural network, and then we go into a bit deeper large language model and see how performances are like differentiating when we go step by step. Now, to give you an overview, as I said, so we'll define it converts, as I said, floating point numbers into lower precision formats, typically integers. Okay, so let me just write it over here. Not exactly that you always do that, but I'm just going to write here. Okay, so you have a floating point number. So you have a floating point, and then you convert that floating point into lower precision format. Those are basically integer. So you convert that in int. Okay, like you can convert 2, 4, 6, 8, 5, whatever bits that you want to convert. Okay, and the benefits, that if you talk about the benefits, it reduces the model size, as we all know. Okay, because lower precision requires fewer bits per number, and it basically reduces the overall model size. So the advantages are, multifold. You reduced model size. So you reduced model size, and then you increased, of course, inference speed. So you increased inference speed, increase inference speed, and then if you go into the third point, which is lower energy consumption. If you want to talk about sustainability, the carbon emissions, and so on and so forth, you bring the energy consumption angle and the perspective into it, right? So lower energy consumption. So basically reduce the computational overhead, translates to lower energy consumption, which is crucial, also crucial for mobile and edge devices, like we like to run it on. If you look at media pipe, for example, so if you look at all these models, let me just write it over here. MediaPipe is a Google product, and they're all using Gemma 2 quantized model through MediaPipe. Runs on mobile devices. I have a video on that. I will recommend you to go and watch that video. Now the next thing is to talk about quantization techniques, and then after that we'll jump into a simple code, and then we'll increase the complexity over a period of time in this video. Now, for you to understand, you should know how many types of quantization techniques are there. So let me just write common quantization technique. So let me just write it over here. Common quantization technique, and the number one we're going to talk about is called PTQ. So let me just write it. So PTQ, which is post-training quantization, and most of the creators like me, the YouTube creators or the people who do not have a lot of infra, we all do post-training quantization. So we call it PTQ, which is post-training quantization. The next is quantization aware training, which is called QAT. So that is nothing but quantization. So let me just write it quickly, and I will give these notes, guys, for you as a reference. You can use this for training, for learnings, whatever. Okay. Now you have quantization aware training, and then the last one, which is very, very critical to understand. I think that's even the algorithms are fascinating to talk about. It's called dynamic quantization. So let me just write it over here. I'll give a quick definitions, and then we'll go into examples and stuff with code. Now, PTQ involves applying quantization to a pre-trained model. So for example, if you take a Llama 3 foundational model, and if you're quantizing it using Llama CPP or AWQ or blah blah blah, those are nothing but called post-training quantization. You are not retraining it. So without retraining, it's quick and easy, but might result in a loss of accuracy. Keep this in mind. Okay, if not done carefully, you will have performance degradation. There is no doubt about it. So people who comes and say, "Oh, you are doing quantization, there is no training, there is no performance degradation," it's doesn't make sense, right? There will be performance degradation. Okay. Now the next is quantization aware training. Now in this technique, the technique that you see, quantization is simulated during the training process itself. So the bigger companies like Meta, the AI first companies, the Meta AI, the DeepMind, the Anthropic, the OpenAI, they quantization is simulated during the training process itself. So this allows the model adapt to the reduced precision and usually results in a better performance compared to PTQ. So they can do it because they have all the infra to perform those tasks. And the last one is dynamic quantization. Now, in dynamic quantization, weights are quantized beforehand, but activations are quantized on the fly during. I think this is one of the best way to balance. Okay, so we're going to talk about it. Now, weights can be quantized beforehand, but activations that you have are quantized on fly. Now, this method method balances performance and dynamic range of activations. This is a bit of theoretical knowledge, and we'll again come back to theoretical in a bit as well. But let's try to see how we're gonna, you know, at least start looking at the quantization from a code perspective. I'm gonna go here on my collab. Okay, so let's import torch. Okay, and you can see I am already on A100 because I will also let you know, or I'll show you from a simple neural networks to a complex large language model how you can quantize. Okay, so let me just show that. Import torch, this all makes sense. So let's get neural network as NN, and I need Optim. I don't need functions for now, the functional for now, so I'll just get rid of this. Torch.optim as Optim, and then torch vision, not import torch vision. I'm gonna do from torch vision. Why would I get all the modules? So from torch vision, I'm gonna import datasets. Well, this is making sense. So import datasets and transforms. Now you can define a simple feed forward neural networks. If you want to do that, probably what I can do, I can go to my GitHub. I have a GitHub gist. I can just go into GitHub. I've created some gist here, your gist, and if I go to gist, you can go to simple just to save some time. I already have some snippets, but we'll write the code also. Now if you look at here, we have a class of, this is basically a very simple feed forward neural network that the beginners learns. You can see we have a linear layer, then we have an activation functions of ReLU, and then we have again a linear, and then a forward where we are just uh, whatever we have defined over here, you can see. And then we are loading simple datasets, managed datasets, handwritten, and let's first run it, and then we go into it. It will download from Jan LeCun's, the yarn.lecun.com. You can see it over here. So it takes a bit of time to get the data in. Cannot get it for the first time. There's something wrong, but this is fine. Now, after that, let's define a model quickly. So I'm going to do is, and this is making sense. So it gives me simple neural network. I'm going to use cross entropy loss and then optimizer. Atom is fine. Model.parameters. Learning rate, let's keep whatever it has suggested. This is not a problem. And then let's define a training loop. So in training loop, I'm going to do for epoch in range 10, not 10. Let's keep it 1 just for the demonstration purposes, guys. And then I'm going to say 2 for epoch in range. Then let's have a model.train here. Okay, so model.train. And after that, I'm going to have a for images and then labels in train loader. This is fine. And then go into your images. So let me just do images equals images dot view. So it's suggesting me images dot view, but I'll have a different dimensions altogether. I'm going to keep 28 cross 28. This is fine. Now, basically, let me just also write it. We are just flattening the image here. So flatten the images. Okay. Now after that, once you have the images, optimizer.zero gradient is right, and then you have outputs model images. This is right. Then loss criteria, outputs labels, and then loss dot backward and optimizer dot step. This code assistant in Colab is working fine, guys. Okay, now let's just run this. And after that, we're gonna do eval. So we're gonna just set the model to inference after this. Let me just do that here. I'm gonna do model dot eval, and inside this, when you do model dot evals, this basically set the model to inference mode, and then you can have a variable called quantized model. And let's use torch dot, you can see it over here, right? So torch has a module that's called torch dot quantization dot quantize dynamic. That's what I'm doing. I'm going to pass model and the linear layer that you see. So nn dot linear, and this is in the training part. So right now we are, for example, if you're training it, okay, nn dot linear, and then you can have a q int 8, which is d type torch q int 8. I think this, let's just run this. This is fine. And now let's evaluate the model. So I'm going to write a function, and we're going to use this function again and again, I think, in this, at least in this video. And I'm going to use model.eval again. So basically what we're going to do is without quant and with quant, we'll just see. And this is a very simple neural network. So you'll see there will be no performance degradation. Accuracy will be same. This is what I want to show you guys. Now total And after that, with torch.nograd, this is fine. This makes sense. Again, for images in for images and labels, and I want to keep the same terminology. So I'm going to call it data loader here. So let's do that. Data loader for images labels in data loader, and then I'm going to pass my images.view. This is fine. And then I'm going to have output model images, and after that, this is making sense. So predicted toast.max outputs.data, this is fine. Then total, and then I'm doing total plus labels.size, this is fine. And then we have correct equal correct plus predicted equals labels dot sum. I think this makes sense, but I'll just make a bit change. I need this in percentage, so let's just multiply this is 100. Now this is making sense. All right, and I'm gonna have an accuracy original variable. Let's do that. And then you're gonna have evaluate model, and then you're gonna pass test loader, and then this will test not test loader. That's gonna pass train loader here, and then again you're gonna pass train loader, evaluate model, and then here you pass the quantized model. This is fine. Accuracy quantized. Let's do this. Oh, excuse me. So I could see it. So here should be data loader because then I just wrote data loader. This is fine. And let me just write the print statement at least. So I'm going to write print original model accuracy, and then you can just pass, accuracy original whatever, and we'll see. We can also round it off, but you will see that there will be not much of performance degradation because it's very simple neural network, a feed forward network that you have. But when you're gonna bit deeper, you will see the you will see the real thing after this. Okay. Now let me just run this. And you can see it says original model accuracy, which is you can look at the model accuracy and the quantized. There's not much of difference. As you can see, it's pretty same. And this is a very simple feed forward neural network where you what you did, you use torch.quantization.quantize dynamic. So on dynamic, we are looking at the linear layer and then just getting in a Q8. So for from floating point to int, okay, lower precision number, and then you can see just how we did it. Now this is a very simple thing. Now we'll go into a bit complex, but let's go back to looking at our, it says connection failed. Okay, I have to connect again. I'll just do a connection. Oh, this is crazy. Okay, so I'll just go in my connection. The issue has been ended. All right. Okay, so let's come back here on the screen grab, and we're gonna talk about a bit. Now, before we go into the next part, increasing the complexity, let's try to understand a bit mathematically, a bit of the concept, because if you really want to join a research team or if you want to work in a very big AI first company, your foundation should be really strong. Otherwise, it doesn't make sense to just go and build a chatbot of using LangChain. Okay, because you don't companies will not need people who can develop a chatbot for them, but they need people who can develop or who can engineer solutions or go into fine tuning or developing LLMs or SLMs in near future, because it will be easy to create their own model in near future. There is no doubt about it. Now, uh, I'll just probably like to explain that quantization involves mapping continuous or the values that we have, the high precision values that into a finite set, okay, of discrete values. And this is generally achieved by approximating the floating point numbers with integers. Keep this in mind. That's what we shown, here with the floating point and int 2468, whatever we have written. So if you mathematically define that, so I'm going to write q of x and then just rounding off. So let me just do round, and then I'm going to write here x minus, and I'm going to explain that what I mean by this 0 underscore point and then by scale. This is what I'm writing now. Scale that you see, so here scale is a factor that scales the floating point. So it's a factor that scales the, let me just write it over here, that scales the floating point number. So I'm going to write fp because you will be using fp16, in your fine tuning. So I'm going to write fp numbers to a new range. That's what the scale is. Okay, that's what scale does. And the 0 point that you see, so here the 0 point is used to match the range of floating points with the range of the target data type, ensuring that 0 in the original distribution is exactly representable. Okay, so this is the basic formula for quantization. Now there can be a symmetric quantization as well, where the 0 point is 0. So if you keep this is 0, now if you keep this as 0, for example, so then your qx become, so qx will become your round of, your round of x by scale. This is how it will work. Okay. Now we can also give some practical example, if we have to do that. Now if you consider, let me just do a through a vector quantization. So we will be probably working with a lot of embeddings model nowadays. And if you, let's say a simple, and these are really intuitive, guys. If you really not interested in learning this, you can just skip to the code, okay, if you want to do that. But if you go through these learnings, you will basically master the foundation of it. Now suppose we have an activations from a neural network layer. Now you have, for example, you have 5 layers, or take a linear layer. So let's say you have a linear layer, and in this linear layer, in this neural network, this is your NN, which is a neural network. Now you have an activation. So I'm going to write here activations, and these activations can be defined like, for example, you have some numbers 1.2, 0.7, or whatever number comes in your mind. Let me just write, and I'll also write 0 here. Okay, now this is your activations. Now you can choose a scale and a 0 point here. Now if to quantize these value to 8-bit integers, how will we do it? So let me just write it here. I'll just give a bit of different colors here, levels here to for the heading. So I'm gonna now write here, and this, let me just call it second. This was your first, and then you are choosing scale and 0 point. So let's say choosing scale and 0 point. This is your second thingy. Now how do you do that? So for simplicity, let's assume, symmetric without a 0 point. So I'm going to do here scale. Let me just do that. So I'm going to say scale equals, and I have a max of my activations. So I'm going to write activations and then just write the number. So for example, I'm going to write to 7, and you can choose the scale, how much it will be. So let me have a look at my scale. So we have activations. If you look at this, blah blah blah. So 1.2, and this will come around 3.5, as you can see in my notes, and then 127. And if you calculate this, this will come around 0.02756. This is what I can see in notes now. And how you can now apply quantization for each of these numbers that you have here. So let's see that. So you have first is q 1.2, and then you have next is q minus 0.7, and then you have q 3.5, and then you have q 0.0. Now here in the q you can have a round of value. So round of 1.2 divided by 0 point, the number that we have got, right? So 0.02756, and probably I don't know how much this will be. So if you, let me have a look. Okay, now this comes around 43.53. If you take the round up, this becomes 44. So similarly, if you do this, This comes to 25, this comes to 127, and this comes to 0. If you calculate, you can also dequantize. You can convert back to floating point for further processing. It basically becomes a dequantization. Now, this is how mathematically you can go into it. You can also code this, by the way. Okay, you can, if you want to do code, you can code it. And if you want to calculate scale, because most of you will have a question that, hey, how can I find out the scale, if you want to find out. So scale is nothing, guys, but you can also write like this. Okay, if you want, just for your simplicity, you can have a range of fe values, which is nothing but the floating point, and then goes range of integer value. So let me just write range of int values here. This is how you define. So for an 8-bit quantization, the int, and you should probably know about it, right? So if you have 8-bit, let me write 8-bit here. Now 8-bit, the integer will become how much? It is between the range of 0 to 255, right? For unsigned integer, or for signed integer, I think I forgot myself. I think it's 128 to 127, right? Uh for signed integer. Now you can have a same quantization functions, round of x by scale plus 0 point. The 0 point adjusts the range to center around 0, and you can have a dequantization as well. This is how you can do it. Now we discussed about it. We'll move into some other techniques, okay, after this. So I just wanted to also explain the mathematical intuitions. It says runtime disconnected. Again, it's connected. I mean, I don't know if it's still working. I have no idea. Let me just get here, refresh, come back. I don't know. I'll quickly run all of this meanwhile, because runtime was disconnected, so imports and stuff will be a bit trouble. All right, let it happen. Now, the next thing, guys, because you will be asking about a lot of questions after this, because you are probably not aware of this. You will be aware of bits and bytes, NFO, double quantizations, blah blah blah. So, what do you mean by that? Okay, so the next is, basically quantization is a very big topic, guys. It's one of the most complex topic to even discuss. And they are really diverse and can range from basic methods like uniform quantization. So whatever we have discussed that you see, these are all uniform quantizations. Okay, and now we are going into non-uniform quantizations. If you write here a non-uniform quantization, and let me just do non-uniform quantizations. Okay, that's and in non-uniform quantization, it does not distribute the quantization levels uniformly across the range of data values. So we talked about the range. So just for your example, just for your information, NF4, for example, I'm just writing a word here called NF4 that you will see in bits and bytes if you are working. And let me just take here, write NF4, which is nothing but called for noise feedback. Okay, and then you have quantile quantization. So I'm writing QQ. We're going to explain this through a code also. Now, uh, there are two types. If you talk about non-uniform quantization, one is called logarithmic. So I'm going to write log quant, and the next is Lloyd max, and I'm going to write Lloyd max quant. Now, this uses a logarithmic scale because you have to use some scales which can be very effective for data with a wide dynamic range. So if you have, for example, if you have audio signals and if you want to perform quantizations, probably you can look at logarithmic quantizations. This is pretty based on probability distribution. So we're going to talk about this, and then we have the other one. We discussed about NF4. It's quantization to improve the quality of the quantization process. By the way, it involves feeding back the quantization error, just like you feed back the loss functions, loss through backpropagation when you work with neural networks. Now here, understand this involves feeding back the quantization error, the difference between the original and quantized value, into the quantization process of subsequent values. So you'll have different layers and so on and so forth. Now, this technique is one of the most important technique, I believe. It helps in mitigating error accumulations and can be particularly useful in scenarios where data is processed sequentially. So this is basically NF4 has been used nowadays with a lot of multimodal LLM, or I'll not write LLM, I'll call it multimodal model, because this works very good with audio or video encoding. So you'll have frames and stuff. So audio and video encoding, and then you have quantile quantization, which is more statistical distribution, It involves dividing the data into intervals that each contain approximately the same number of data points. This method also ensures that quantization adapts to the data distribution, which can be useful for non-uniformly distributed data. Now let's look at how we can, implement a quantile quantization using, Python. If you wanted to do that, you can also do it in C, C++. That will be a bit more low level. So let's go through it, and then we can go into a bit complex topics. Now I'll go back here, and here I'm going to write few things. Let's have numpy. So I'm going to write import numpy as np, and then I'm going to define a quantile quantization, and then I'm going to have number of bins, and then in quantile quantization I'm going to have a quantiles. So you're going to have different the beans that you are having for the quantiles. I'm going to have np dot. So numpy has a module called quantile, and you can see it over here. It's take data. I'm going to have a linear space, so and then pass. I think this is making sense to me. I'll just keep as it is. Now we have to adjust the indices from 0 to number of beans minus 1. So how will we do that? Okay, so this is not making sense, but what we're going to do, so we have quantized data, np dot digitize data quantiles, and then I'm going to write here minus 1, and then I'm going to just return quantized data and also the quantiles. Not the quantized. Okay, so I'm going to write quantiles, and then np.random.randin, and then let's have some normally distributed data. 10,000 will be a bit high. I'm going to keep it 1,000. np.random.randin, and we're going to have, let's have a number of bins. So I'm going to define number of bins here, and then I'm going to write 10, and then here you just write number of bins just for a better understanding. Quantize data and quantiles, I'm going to use quantile underscore quantization, this function, and then I'm passing the data and number of bins. Let's run this, and I'm going to have print here, print quantized data, and what else? So we have quantized data, and let's not print all those. Okay, so I'm going to print and then quantiles. This looks good. And you can see this is your quantized data, and now these are your quantiles. Okay, this is how you can implement quantile quantizations as well. But now I let's go to the move to the next important topics, moving into the language models, because that's what you would be interested in, and I know that. So let's move into examples of quant through language model, and we're going to increase the complexity. We're going to start with a simple language model and GPT-2, and then Llama 3 or Phi 3, whatever we'll see. Okay, now a language examples of quant through language models. uh, I have a gist. I'll just go back just to save some time. Okay, and I'm going to use lm.py. I'm just going to let's go into raw and get all the things done here. So control A, control C, come paste. And you'll see that even for this your accuracy is same, so there is nothing changed. Okay, and this is very simple, where you can see what we are doing. So we are initializing the model, a very simple feedback forward model. The same thing, character-based data sets. We have a data sets which is on based on characters that we have just generated, and you can see the same accuracy. So even till now, we don't have any performance degradation. We're gonna move into transformer based. So let's just quickly move to transformers, BERT based or whatever. I'm gonna just write it over here, and then I'm gonna write from transformers import BERT tokenizer. So let me just do BERT tokenizer, BERT for sequence classification, and then I'm gonna pass from torch dot, excuse me, torch dot quantization, and then import quantized dynamic. And then let's load a model. So I'm gonna do is I'm gonna load a model. So let's just get BERT. Yeah, this was making sense. BERT base uncased, and then you get the model from BERT for sequence classification. This is making sense. I'm just gonna load this. It'll take a bit of time. Notebook does not have grant access. Oh, do I need a? Oh, all right. Do I need to log in with the notebooks? Probably not. and then we're gonna encode blah blah blah, and then we will see a few things here quickly. Now you can see we are done with the model. So let's have an example text. So the text I'm gonna write is uh, hello, probably how are you doing today? And then we're gonna have an input tokenizer text return tensors, and then I'm gonna write truncation, and in truncation equals true, and then max length. Let's keep a max length here, and in the max length I'm gonna pass 512, and then input is fine. I'm gonna remove the output from here for now. Let me just do that. Input is fine, so we have encoded. Now what I'm gonna do is we're gonna perform inference before quantization. So we torch no grad outputs. Let's call it original. So original outputs, and then I'm gonna pass original output model inputs, and then just run this. And once we run this, and now we're gonna apply the dynamic quantization. So let me just write apply dynamic quant, and for that quantized models, quantized dynamic model. I'm not gonna pass here nn dot linear only. I'm gonna pass because if you look at the above code, which is torch dot nn dot linear and d type torch q end. So the same thing, and quantized model, and on the same now I'm going to do inference with the quantized model. You can see quantized output, quantized model inputs, and then just going to print it. So let's just print our thingy here. So print original output, and then print quantized output. You can print the logits. Better do let's print the logits first. Okay, let's just do, and we'll find out if it gets the same numerical representations. And you can find out no, do not have the same. Okay, so this is what you can see, and now you can how you can save this quantized model. And if you want to do that, this is a very simple one for transformer based. So this is how you can use torch.save. So let's use torch.save, and you're gonna pass quantized. So let me just do that here. Quantized model.state dict, and then you're gonna pass you know a model in PTH. This is fine. Let me just do that here. And if you refresh this, you will have something over here. You can see that you have saved something, which is bird quantize.pth. You can also use save tensors to do that if you want to do it. Now, how can you load the quantized model? So let me just write it here. Load the quantized model, because you like to do quantization and then load it again, right? Now, to load the quantized model, I'm going to write model loaded equals, and then use bird for sequence classifications from pre-trained, and then the model name, and then model loaded. Uh, not this is how I'm going to do. So model loaded equals, and then I'm going to pass quantized dynamic. Yes, quantized dynamic, and then model loaded, and then I'm going to pass torch nn dot linear. We're just reapplying the quantization. If you look at here, let me just write it. Reapply quant, and d type torch q index is fine, and then model loaded dot load state dictionary, torch dot load, and this is the model. This is fine. This is fine. Now I'm going to do is perform the inference. So let's just do model loaded dot eval, and with torch dot no grad, and then I'm going to have loaded output, model loaded inputs, and then just going to print. So let's just print the thingy here. So print original output and loaded output dot logits, or just you don't need this. Okay, let me just remove it from here, and you can find out a tensor. You can see it over here, the same thing that we had. So this is how you can also save it and then load it. Let's move into a bit complex again. So we increase the complexity now. So what I'm going to do, so let me just do right here GPT-2. So let me just write GPT-2. So now we're going to look at GPT-2, and for that I'm going to have from transformers import GPT-2 LM head. This is fine, and then I'm going to have import time, because I'm going to compare now. Apologies for the background noise, guys. Okay, the weekend happening, the party is going on. So now the next thing is model name. So we're going to GPT-2 tokenizer, GPT-2 tokenizer dot from pre-trained. This is fine. Model name, model is fine, and let's just do model.eval. Model.eval, and let's just run this. Now once you run it, it's going to get it here, and then again we're going to follow the same step. So we'll just do, let's have some simple text. So I'm going to have an input text, and remember GPT-2 by OpenAI before ChatGPT. Input ID is tokenizer dot encode. We're going to encode this input text return tense of pt, and then let's just run this. Now we're going to measure the performance before quantizations, and of course we're going to apply dynamic quantization here. So let's have a start time. So start time equals time dot time, and let me see. So with torch dot no grad, this is fine. So I'm going to have an, let's write an original output. So original outputs equals model dot generate, and then you're going to pass input ID max length. Let's reduce that 50. And keep this in mind, guys. GPT-2 generates, so it has the generation ability. Now, original output is fine, and I'm gonna have here your original duration. So original durations equals time dot time. This is fine, which is start time, and then have your thingy, which is original text, and which is original text. So you're gonna do tokenizer dot decode original outputs, skip space search tokens too. This is fine. Now let's run this and see. And if I just gonna write here original text, you can see the I'm sorry. I don't know. They asked GPT-2, and now I'm gonna apply dynamic quantization. So let me just do apply dynamic quant, and I'm gonna have quantized. I'm gonna have quantized model. So again, not this one, not this one. So I'm gonna remove this, and I'm going to write torch dot quantization. This is right. So quantization dot quantize dynamic, and then you pass the model torch dot nn linear, and this is what I need. So let me just do this. And then you move into quantized model dot eval, and you can see it will give you, you can find it out over here. If you look at the last one, if you look at this LM head, it says dynamic quantized linear. You can find it out over here. Now this is great. You can look at this, that's what not there. So this is the change that we have make. Now you can understand where we started. So we started with a simple feed forward neural network, then we looked at a BERT model, then we're looking at GPT-2, and now we'll move to, after this we'll move to 5.3 or something like that. Okay, now we're able to get this. Now after this you can measure the, the same, let's just do that over here. So I'm going to do is start time. Okay, so time dot time with torch no grade, quantized outputs, quantized model dot generate input IDs, max length, and then you can just pass quantized durations, time star, this is fine, and then quantized text, tokenizer dot decode, quantized outputs, this is fine, and you can print the original as well. So let's just print that here. So print, and you're gonna print original text and print quantized text. And you can find it out over here. Okay, generating something garbage, but it is fine. This is what it does. Now it generates some garbage and stuff, right? Now you can see now GPT-2. Now let's move into something complex. So I'm gonna move into 5.3, and I'm going to show that via X. There's a Python library called xllama v2. You can use multiple libraries to quantize. You can use GPTQ, you can use no, not GPTQ, I've said llama CPP, and you can also use ollama, you can use xllama v2. There are a lot of supports, but for this let's just do that. So I'm going to do pip install, and I want to keep all. So we're going to install three libraries here. So I'm going to do bits and bytes and accelerate, and then datasets. Let's download it, install it, and then I'm going to do a few things. So first is import torch, and then from transformers import auto tokenizer. So let's just do that. So I'm going to do auto tokenizer, auto model for causal LM, and then bits and bytes config, and you can find it out over here. I'm going to keep writing in this only. So I'm going to do if torch.cuda, this is fine. uh not is available, so what I'm going to do is if torch.cuda is bf16, right? bf16 supported. So I'm going to just change the game here. So I'm going to say bf16 supported. I'm on a100, so I believe it supports. So BF16 is supported on A100, and then I'm going to remove this guy from here, and let's write compute D type, because I'm going to select my D type. So if you compute D type, then BF16, else then you use the compute type as floating point 16, just because, just to for the memory and stuff. So this is fine. We are good with this. Model name. So let me just write here model name, and we're going to use not quant. I'm going to use phi3. So let's just write here phi3 mini mini 4K instruct HF blah blah blah. Okay, come here, just copy this. Uh, Probably we can work with this guy. Okay, so let me just copy it here, pass it. So we have Microsoft Phi 3 Mini 4K instruct, and after that I'm gonna pass my quant path. In quant path, I'm gonna write. You can write something. So let's just do Phi 3 Mini 4K quantization. I'm gonna write this. Okay, and you can do 4-bit or something. Okay, now quantization is done, and then you need tokenizer. So let's get tokenizer. So tokenizer equals auto tokenizer from pre-trained model name. You have to do trust remote code true for this. So let's just do trust remote code true. To not model as of now, I'm going to define a BNB config. So let's just do BNB underscore config. And in BNB config, you're going to define bits and bytes config. Inside this, you are going to pass. Are we going to load the model in 4-bit? So load in 4-bit true if you have memory constraint. If you don't have sufficient VRAM, so load in 4-bit true. And this is where I'm defining NF4. You can see it's a data structure, guys. So BNB 4-bit quant type, which is a NF4, and then I'm gonna pass my BNB use double quantizations true and then compute D type. And I think I'm good with this. And then I'm going to load the model with the help of uh, BNB config, and you can just do trust remote code true, whatever. Probably I think I have to log in if I'm not wrong. Okay. And then what I'm going to do after this is model.save. So you have to save. If you want to use xllama, you have to save the model. Okay. And I don't probably recommend if you have a bigger model to save, but you can save. So quant path, and let me just do it a bit different. So what I'm going to do is the quant path and then safe tensors. So I'm going to do, yes, safe tensors, my friend, safe tensors. Okay, safe tensor. This is where it fails. So safe tensors, and then you're going to write true, and then tokenizer. So tokenizer dot save pre-train, and then you just do plus quant path. I think this is fine. Now, guys, this is going to take a bit of time, so probably I can pause the video here and come back once this is done. Now, as you can see that we have successfully downloaded the model here. You can see Phi 3 Mini 4K quantization 4-bit. We have whatever we need over here. You can find it out here, blah, blah, blah. Now, what we're going to do next is we're going to install a couple of more libraries. So let me just do that. So I'm going to do pip install, and I need Auto-GPTQ. So let me just get that. So if you look at GPTQ, GPTQ is, if you look at GPTQ, let me just show you here on GPTQ, or if you look at the library itself, Auto-GPTQ. Now come here, and if you look, it says an easy to use LLMs quantization package with user-friendly APIs based on GPTQ algorithm. So you can find it out over here. This is the library that we're gonna use, and easy to use LLM quantization, the same thing, weight only quantization. So I discussed about that. If you remember, weight we discussed on the in the beginning that we're going to only talk about. So there are three different types: post-training quantizations, quantization aware training, and dynamic quantization. And it only looks at weight only and not on anything else. Okay. And you can find it out here if you want to read more, how you can quantize it on a single GPU and stuff. Now, here I'm going to install Auto GPTQ and Optimum as well. Optimum, by the way, also helps you with evaluation. So Optimum is a different Python library. So let me just show you Optimum GitHub, and you can find out accelerate training inferences of transformer and diffuser with use and optimization. And you can also use this for evals as well. They have also have evaluations, and you can see the accelerator Onyx runtime, Intel neural compression to run it on CPU machine, Open Vino by Intel again, NVIDIA Tensor RT, blah blah blah. So you can use Optimum to basically, this is the framework that helps accelerate on different platforms and you know uh, hardwares. Now what we're going to do here is that we're going to use the same thing. So from transformers, again going to import this. You can run it separately as well if you want to do it. I'm not going to use Onyx runtime. I'm going to use GPTQ from Optimum. And in GPTQ, I'm going to import here GPTQ quantizer. Okay. So let me just do GPTQ quantizer. And then I'm going to have import torch. all of these cells you can run it separately, guys. So let me just do that. Now here I'm going to define model path, and you know the model path. So let me just get that from top. We have our model path. I'm just going to get this from here, and also let's get the model path. And two, this is my model name, model path. So this is your model path. And after that, what we're going to do here is, let me just do model path. And here you can define your what is W. Now W is quantization integer value that you define. So when I'm writing 4, it means the quantization to 4 bit. Now if you want to do all at once, like then you have to do it in a list. So you need to define in a list 2 4, 3 8, whatever. You can define it like this and you can do it. But I'm just doing it just to show you that how you can do it. You can also use other precision as well if you want to do that. And then you're going to write quant path here. So in quant path, I'm going to write the same thingy. So I think it's okay. You can see 5.3 mini 4K quantization 4 bit, whatever it's showing. But I'm going to make a bit of change here. So I'm going to say, hey, look, 5.3 mini 4K instruct. Let's write instruct. And then I'm going to write my GPTQ. Okay. So GPTQ. And then I'm going to also, and let me make it a single code for this. And what I'm going to do, I'm going to string the bit, so which is W and then the bit. Okay, now this is my quant path. Now next is I'm going to load the model and tokenizer. So let me just write load model and tokenizer. Okay, now here I'm going to define tokenizer auto tokenizer dot from pre-trained model path, and you can use some params like use fast. It has use fast, and I'm going to do use fast equals true, and you can do trust remote code. So trust remote code, and you can keep true. If you don't keep true, it will ask you, it will prompt you for putting that there. And then for the model, you're going to define a torch d type. Okay, so torch d type torch dot, let's keep it float 16, uh, and then trust remote code is true. Then you can keep a device map auto. We are already on GPU, so let me just do a device map equals auto thingy here. And then this is making sense now. You have trust remote code. This is fine. Pre-train auto model, causal LM from pre-train. This is all nice. Okay, let me just put here. And then you have a quantizer. So in quantizer, here I'm going to use GPTQ quantizer, and you're going to write bits equals W. So what bits? Remember the way we also do it earlier. We were defining Q int 8. Now here I'm defining bits W, and then I'm writing data set of, it has a param called data set. You can read about it. And then I'm going to have a sequence length of model. Remember we did it earlier as well. We're keeping it very less, but here we have to keep it a bit high. So model sequence length, it has something over here, and you can just do something like a very decent 2048. And after that, quantized model. So quantized underscore model equals, and you can just do quantizer. So quantizer dot quantize underscore model, and here you're going to pass your modeler and tokenizer. So let me just do that, model tokenizer, and I think we are good with this. So model tokenizer, and then you just do quantized model dot say pre-train, and then you're going to pass your safe tensors. Okay, so safe tensors equals true, and then this is making sense. And then you can do tokenizer dot save pre-trained, and then you can just save this. Let's save it and see what happens. And guys, I have a couple of videos on this topic already, a very detailed video. You should also watch that. I have a video called Quantize Any LLM. I will give the link in description. You should watch these videos. But you should watch this video first now, because this is like a crash course where we start with a simple neural network in PyTorch, and then we go into BERT, GPT-2, and then now using libraries like Auto-GPTQ. You can use this library to quantize model. You can see Auto-GPTQ, and you can also use Optimum that will help you accelerate. It's an extension of transformer, and also diffuser if you are in the media generation kind of models. And it provides you a set of optimization tools, and you can see it over here: on time, Auto-GPTQ, blah blah blah. Now everything is here that you can read more. This is a great library, guys. You can see this is what we have tried, quantization aware training, post training, dynamic quantizations. We discussed about that in theory when we were reading post training static quantizations. We have covered this all. FP16 half precisions, blah blah blah. Okay, this is the library that you should try it out with Optimum Auto GPTQ. And it takes a bit of time, but now you got the idea, right? You got the gist of it. It will all be stored here. In a We have everything. You can see bird quantize. Now we have 5.3 that we've downloaded. We'll also have a new folder for this one. And you can push it to Hugging Face as well. You can use Hugging Face API to basically upload these files, push it there with the Git LFS and whatnot. I have shown this in all of my previous videos. Okay, but this will gonna take a bit of time. So anyway, let me just pause the video and come back. As you can see that our model has been quantized, and it's now here in this folder called 5.3 mini 4K quantization 4-bit. And when you expand that, you will only see the safe tensors. Okay, now you can push this model entirely on Hugging Face, using your Hugging Face API keys. You can push it there and you can load it and use it, deploy it on SageMaker, RunPod, Inference API, and wherever you want to do that. So this is how you can do it, guys. There are n number of other ways to quantize LLMs nowadays. There are lot of libraries that you can do. I have shown this now with uh, Auto-GPTQ, Optimum. I have shown this earlier with Llama CPP as well. Feel free to use this library. You need XLlama V to download, and you can do that. Now, we started with a very simple thing. We started with a simple neural network. Then we moved to a language model based on characters. Then we tried a transformer based BERT model. Then we tried a GPT-2 with dynamic quantization. And then we looked at Phi-3 using some libraries and frameworks. I hope you found this tutorial helpful. And this concludes our experimentation with quantization of language models. That's all for this video, guys. I hope now you have basic understanding of quantization and how you can quantize neural networks, how you can quantize language models and large language models of different types. You can look at bot-based transformers and GPT-2 and the uh, newest of LLMs having encoders, decoders, whatever. Okay, now it depends on what kind of problem you are solving. Quantizations are of different types that we see. Post quantizations, training aware quantizations, or basically quantization aware training (QAT), and then dynamic quantizations. Now, I'll give this code in my GitHub repository. I'll give the link in description. I'll also give you the screen grab of the a bit of theory that we discussed for your references. And there are other libraries that you can also explore that we also saw in this video: Optimum and AWQ, Llama CPP, OLlama. You can all explore these libraries. Okay. Now, if you have any questions, thoughts, or feedbacks, do let me know in the comment box. You can also reach out to me through my social media channels. Find all the information on channel banner and channel about us. If you haven't subscribed the channel yet, please do subscribe the channel. And if you like the content, please hit the like icon and share the videos and channel with your friends and to peers. Thank you so much for watching. See you in the next one.